Hi, everybody. Thanks for tuning in. My name's Dylan Amaya. I'm a research scientist at the NOAA Physical Sciences Laboratory in Boulder, Colorado, and I'm excited to talk to you today about subseasonal to seasonal forecast skill in the California current system and its potential connection to coastal Kelvin waves, an example of what you're seeing in this animation on the right side of the slide here. So the California current system is home to the California Current Large Marine Ecosystem, which houses a diverse array of important marine resources that present a variety of different management challenges. And these management decisions could really benefit from accurate forecasts of ocean conditions across timescales. And historically, most of the scientific focus has been on assessing seasonal forecasts within this region, and probably for good reason. We'd expect most of our dynamical forecast skill to happen on these seasonal timescales, especially because the ocean is so sluggish and it has such a large thermal inertia. But there are important management decisions that are being made on sort of these 1 to 60 day timeframes, sort of this subseasonal to seasonal timescale, that could benefit from a dedicated focus from a forecasting perspective. So, for example, managers are trying to reroute shipping lanes to minimize or avoid ship strikes of large marine mammals, or rerouting fishery efforts to overall minimize bycatch. So we could use, and we probably need, to begin to evaluate ocean forecast skill on sort of these S2S timescales, particularly in this region. And if we're thinking about how to approach an S2S forecasting system, we can really lean into what we've learned from seasonal forecasting assessments, which is that forecast skill is often conditional on physical processes that drive observations. So there could be something deterministic or something dynamical that is driving the trajectory of observations that, if the model can simulate that very well, and if it's part of the initial condition, then that can often lead to a better or more skillful forecast. So it's fair to think, what physical processes that impact the California current system are occurring on sort of these subseasonal to seasonal timescales. And obviously one well-known physical process that is coming from, say, the tropics, where we get a lot of our deterministic forecast skill, are atmospheric teleconnections associated with ENSO or BMJO, where we get large-scale deep convection in the tropics, and that drives a Rossby wave train through the atmosphere that adjusts winds along the California current system and can ultimately change ocean conditions. But perhaps a more overlooked or a different teleconnective pathway that could provide forecast skill on sort of S2S timescales are ocean teleconnections associated with intraseasonal ocean Kelvin waves. And just to give you an example of what one of these coastally trapped waves might look like, I'm showing you an animation of sea surface height anomalies during the development of the 1997-98 El Nino. You'll be able to see this coastally trapped wave as it propagates up the North American coastline as an elevated sea surface height signature. You'll see that it slithers up the coastline and ultimately elevates sea surface heights in the California current system right along the continental shelf. And that's really what we're going to be looking at today. We're going to look at dynamical forecasts of California current system sea surface height right along the coastline, and we're going to ask the question of whether these forecasts are skillful on subseasonal to seasonal timescales. And then, having done that, we're going to ask the question, do coastal Kelvin waves that are propagating through the California current system, do they provide an opportunity for an enhanced forecast skill, particularly when the forecasts are initialized with an actively propagating wave? In order to assess the skill of our dynamical forecast of sea surface height, we need some baseline, some measure of truth. And for the purposes of our study here, we're going to be using this Glorious Mercator ocean reanalysis as our measure of truth. This is a very high resolution ocean reanalysis with 1/12 degree horizontal resolution. Here's some general information about this Glorious reanalysis. But again, we're primarily going to be focusing on sea surface height. And I'll just say that Glorious compares very well to independent observations within the California current system, specifically tide gauges. Glorious does a very nice job of capturing both the day-to-day and month-to-month variability of sea surface height measured at tide gauges when you compare it to the nearest grid cell. So we're comfortable in using Glorious as our metric for truth when comparing to our dynamical forecasts. And here's some information on the dynamical forecasts that we'll be assessing today. We're going to be looking at the ECMWF S2S forecasting model, which is a coupled model that has both atmosphere and ocean hindcasts or reforecasts. And for the ocean, the reforecasts are for 46 days. They're initialized every 3 to 4 days beginning January 2nd, 2000. So between 2000 and the end of our comparison period in 2018, we have about 2,000 forecasts to assess. Each forecast has 11 ensemble members, and we're going to primarily be focusing on the ensemble mean of those different ensemble members. The forecast skill for sea surface height will be assessed using correlation squared, or R squared, in these different California current system subregions, which are shown by these different colored boxes here in this map. Each box is showing you the coastal grid cells, the 1 by 1 degree grid cells in the S2S forecasting model. And basically what we'll be doing is averaging the sea surface height in each of these different subregions and comparing them to the GLORIES data averaged in the same subregions in the same boxes. But the GLORIES is obviously much higher resolution, so we're going to be focusing really only on GLORIES grid cells with ocean depths that are shallower than 400 meters, which is showing you, which is shaded in red here. So really just focusing on the continental shelf. And then finally, the forecast scale will be compared against damped persistence. And for a dynamical forecast to be useful or to be considered skillful, it will not only need to have a significant correlation, so significantly above zero, but it also needs to be significantly different than persistence. Otherwise, persistence is your better forecast, and you might as well just be using that. All right, so here is the overall skill assessment in each of these different California current subregions. We're showing you this forecast skill as a function of lead time on the y-axis and initialization day on the x-axis. The shading is showing you those R-squared values, and the stippling tells you some interesting things. No stippling actually indicates a significant R-squared value above zero. Black stippling tells you that the R-squared value is not significant, and red stippling is actually telling you that the R-squared value is both significantly above zero and significantly better than persistence. So it's those red stipples that are going to indicate whether the dynamical forecast is useful and better than that statistical forecast that we use from persistence. So a few features worth pointing out here. If we look at, say, the Southern California current system first, we can see that the R-squared values overall are quite high. However, if we zoom in and just sort of focus on this time period and these lead times, we can see that the dynamical forecasts begin to be significantly above persistence at relatively longer leads. So after about week 2, so about 15 days to 20 days out. And when you initialize, specifically when you initialize the model in the summer and in the fall. And this is interesting when you compare these results to something like the North California current system, which is very different. You can see that the forecast skill is much lower throughout the Northern California current system. You can see these greens and lighter blue colors. And you also see that there are significant dynamical forecasts above persistence at earlier lead times. You can see all these red stipples here. The reason for this is actually pretty interesting. There's quite a bit more weather noise in the Northern California current system than there is, say, in the Southern California current system. So as a result, there is much more persistence in the south and much less persistence in the north. And this does a couple things to your forecast skill. In the Southern California current system, it takes much longer for the dynamical forecasts to begin to separate from persistence because there is such strong day-to-day persistence in this region. Whereas in the Northern California current system, the increase in weather noise will actually lower your dynamical forecast skill overall because weather noise is random. It's very hard to predict in a dynamical forecasting system. However, what that also does is it decreases your day-to-day persistence, making it easier for your dynamical forecast skill to become better than persistence over time. So it's really this weather noise that's driving what we're seeing here in the Northern California current system relative to the Southern California current system. So I hope you can see from this figure here that there is some dynamical forecast skill in each of these regions, depending on what lead time and what initialization day you're looking at. So now the question becomes, if we think about Kelvin waves as they're propagating through these different regions, are forecasts that are initialized with strong Kelvin wave conditions, do these forecasts have enhanced skill? Are they better than forecasts without Kelvin wave activity? So to answer that question, we need to be able to characterize coastal Kelvin wave variability throughout our record so that we can then go back and look at our individual forecasts and determine if they were initialized with active Kelvin wave conditions or non-active Kelvin wave conditions. And then we can compare the forecast skill between those two groups. So to do that, we're going to develop a coastal Kelvin wave index, and we're going to use the GLORIES ocean reanalysis product to accomplish that. Basically, what we're going to do is we're going to take sea surface height anomalies along this red pathway here from the western equatorial Pacific to the eastern equatorial Pacific and then along the North American coastline, tracing the typical pathway that is taken by an equatorially trapped Kelvin wave generated by, say, a westerly wind burst that makes its way all the way across the equatorial strip, running into the South American coastline, and then converting its energy into a coastally trapped wave as it propagates up the North American coastline, and ultimately entering the California current system. So basically, we're converting our sea surface height data into from a 3D physical space from time lat lon into a 2D physical space of time and then distance along this pathway that is traced by the red shading here. And so ultimately, what that looks like is a Hofmüller diagram of this wave number and time filtered sea surface height anomalies along that physical pathway following the coastally trapped Kelvin wave path and then throughout time. So I'm just showing you an example of one particularly active Kelvin wave period during the development of the 2015-2016 El Nino. And I'm showing you the sea surface height anomalies associated with many downwelling Kelvin waves that are making their way from the western equatorial Pacific all the way to the eastern equatorial Pacific, where they run into South America, continue up the coastline, enter the Gulf of California on the east side, exit on the west side, enter the California current system, and then ultimately cross the Canadian-US border here. And so you can see the distance that these Kelvin waves are traveling, ultimately traveling something like 30,000 kilometers over the course of about 120 days as they go from the western equatorial Pacific all the way to the Gulf of Alaska, and really propagating at fairly consistent speeds of about 2.7 meters per second. So really remarkable features that we can see here in this high-resolution ocean reanalysis. And so now we're going to be able to use this 2D physical space, and we're going to be able to calculate a coastal Kelvin wave index using a variety of different EOF methods. And this EOF analysis will represent the extension of some previous work done by Rydbeck et al. In 2019, in which they took the first two EOFs of wave number and time-filtered sea surface height anomalies in the equatorial Pacific along 2 south to 2 north. And basically what they showed is that those first two EOFs are phase-lagged relative to one another, and they represent the eastward propagation of equatorially trapped Kelvin waves. And so they developed an equatorially trapped Kelvin wave index represented by the amplitude and phase relationship between these two PCs. And this is exactly analogous to, say, the MJO literature, which has a variety of different indices that are based on pairs of EOFs. And so what we're going to do here is we're going to extend this analysis to not only include the equatorial strip, but also coastal grid cells in our GLORIES ocean reanalysis. So we're going to repeat the EOF analysis in 2 additional domains, one including the entire Kelvin wave pathway that you saw on the previous slide, so all the way from the western equatorial Pacific to the Gulf of Alaska. And then again, we're going to repeat this analysis using only coastal grid cells. And the reason for that is because not all coastally trapped waves originate from the equatorial Pacific. Some of them are locally generated by random wind variability. So it's possible that different pairs of EOFs in different domains are going to have different amplitudes that represent different forms or different flavors of coastally trapped Kelvin waves. And we want to see if any one of these indices is representing the full spectrum of flavors of Kelvin waves that might be influencing the California current system. This figure shows sea surface height anomalies along our Kelvin wave pathway regressed onto the first 2 PCs of each pair of EOFs within each of the domains seen on the previous slide. For example, in the top panel here, you're seeing the sea surface height anomalies associated with the first 2 EOFs within our equatorial-only domain. And comparing to the Rydbeck et al. 2019 results, you see a very similar set of EOF patterns where we have this dipole in EOF1 and a monopole in EOF2, and each of these EOFs are phase-lagged relative to one another in time, indicating this positive along-path propagation of an equatorially trapped Kelvin wave. And what's interesting is that when you start to include more of the coastal grid cells in either our equatorial plus coast domain or our coast-only domain, you'll see how the EOFs begin to project more strongly up the coastline. In particular, in the coast-only domain, you can see a much stronger projection of sea surface heights anomalies within the California current system itself, indicating that the coast-only domain is more strongly capturing coastally trapped waves that are propagating through the California current system. In taking the amplitude of each pair of PCs, we're able to create an index that represents the strength or intensity of Kelvin wave activity in each of the domains. But given how strongly the sea surface height anomalies projected up the coastline in the coast-only domain, particularly within the California current system, we're going to be using this index as a means to stratify our dynamical forecasts into forecasts that were initialized with and without strong Kelvin wave activity. And now finally, we can show you the dynamical forecast skill as a function of lead time, now aggregated to weekly leads, but also composited based on Kelvin wave intensity at forecast initialization based on the amplitude of the coastal Kelvin wave index shown in the previous slide. So right here, I'm just showing you an example from the South California current system. The dashed lines show you the persistence forecast skill, and the solid lines are showing you the dynamical forecast skill, where the filled dots indicate that the dynamical forecast skill at that lead time is significantly better than the persistence forecast. And the different colors of each line are telling you some information about the kind of Kelvin wave intensity at forecast initialization for the given composite. So, for example, the blue line is indicating a composite of 928 initialized forecasts that were initialized without significant Kelvin wave activity. whereas the yellow, orange, and purple lines are indicating composites of forecasts that were initialized with some amount of Kelvin wave activity, ranging from weak Kelvin wave activity out to what we call extreme Kelvin wave activity. So let's just very quickly summarize what we're seeing here. For one thing, we are still seeing significant dynamical forecast skill, just in general, from weeks 3 to 7, where we're seeing that the dynamical forecast system can explain something like 30 to 40% more of the sea surface height variance in the observations than just a pure persistence forecast. So right there, that's a feather in the cap of the dynamical forecast system. It seems to be doing something good. And now on top of that, we can see that when coastal Kelvin wave activity is present at initialization, we're seeing enhanced skill ranging from about 6 to 10% more variance explained relative to dynamical forecasts that were initialized without significant Kelvin wave activity. And while I don't have time to go into detail for each of the other subregions, I'll just mention that the results are generally consistent, particularly in the North California current system. And with that, I'll just very quickly summarize. We showed that the ECMWF model has dynamical forecast skill of coastal sea surface heights throughout the California current system on S2S timescales, particularly in weeks 3 to 7. We also showed that generally forecasts that are initialized with active coastal Kelvin wave conditions tend to have enhanced forecast skill, indicating that coastal Kelvin wave conditions might be used as a forecast opportunity for future management decisions. And then finally, if you're interested in using this coastal Kelvin wave index for more analysis or for future understanding, we do intend to make it online soon, hopefully on the NOAA PSL web servers. So stay tuned for that. But with that, thank you for your attention. Please feel free to check out our published paper on this topic if you're interested in more of the nitty-gritty details. Otherwise, I look forward to meeting and talking with more of you soon. Thanks.